Hello everyone, this is Ahmad Shboul, a postdoctoral researcher in the group of Professor Ricardo Izquierdo at ETS, École de Technologie Supérieure in Montreal, Canada. Today I'm happy to share with you my advancement to develop hydrogen sulfide gas sensors for food packaging and healthcare applications. One of the most frequent questions that people ask me from outside the sensors field is, what is the reason behind the huge interest in sensors? Although the question's simplicity, I think it is essential, and I want to take the chance to answer it. The timeline of the Industrial Revolution outlines the major inventions that made significant shift in human lives, starting by the creation of machines throughout the technological and digital revolutions. And now we are living in the fourth industrial revolution, the smart factory, or as called Internet of Things, where machines are interconnected and automated. This rapidly growing technology combines between sensors and electronics. Sensors collect the information from the physical systems to then manage and process locally. Then, throughout the network layer, the information is sent to the application layer for their implementation in their respective fields, such as buildings, home, health, transportation, industry, and others. As a result, we started hearing about smart portable and medical and healthcare devices and smart homes. So as we can see, the development of sensors are an essential element for successfully develop this technology. And this is the reason behind the huge interest and for the big events organized or for the big journals that focusing on sensors development. Taking part in this development, we are a chemist and engineers in the lab of Professor Ricardo Izquierdo, who are working together to develop disposable sensors from nanocomposites and printed graphene films for food packaging, healthcare, and environmental applications. In one of my projects, I'm developing hydrogen sulfide gas sensors for healthcare and food packaging applications. Hydrogen sulfide, which is well known as poisonous gas, can be produced by volcanoes, eruptions, and mining activities. It is also produced by the degradation of organosulfur-rich foods or by the bacteria activity in mouth. So as a result, it opened the gate to use hydrogen sulfide gas sensors as electronic nodes to monitor the gas development and therefore determine the level in the degradation level in food or the bacteria activities in mouth. We printed our sensors from a nanocomposite that includes iridium oxide nanoparticles, graphite flakes, and polystyrene. The preparation procedure is very simple. That depends basically on the simple string of the nanocomposite components. Then using the doctor plate to coat the nanocomposite in top of carbon bars, which is screen printed in top of flexible substrates like PET. And by using moderate drying temperature of 40 degrees for 1 hour to have the sensor. For more details, I advise to go to our publications in IEEE sensors. We investigated the development on sensors sensitivity step by step. By starting by sensors based in pure iridium oxide nanoparticles, they were sensitive to 1 ppm gas concentration. By the addition of graphite, these sensors became sensitive to 0.5 ppm, which we attributed to enhancement on the volume to surface ratio that enhanced the gas penetration to react with the reactive sites in the sensor's bulk. And in this SEM image, it shows the enhancement in the nanoparticles distribution in the sensor's surface compared to the compact structure for iridium oxide-based sensors. By modifying sensors by polystyrene, which we added to enhance the nanocomposite integrity and adhesive properties on the substrate, it also helped to improve further the gas sensor's sensitivity to detect 100 ppb of gas concentration, which we attributed to further enhancement in volume to surface ratio. In this work also, we showed the capability to manipulate sensors' sensitivity to humidity. So for example, for sensors based in iridium oxide nanoparticles, they were responsive to humidity change. By addition of a graphite, which is a hydrophobic material, sensors sensitivity reduced greatly to humidity change. And by addition polystyrene, which is another hydrophobic material, we could reduce further sensors sensitivity to humidity change. Thanks to polystyrene, which worked as a gas membrane to distinguish between hydrogen sulfide and water molecules, we could reduce sensitive sensors to 100 ppb while they are resistant to humidity change up to 93%. Although the good development of the sensor, its sensitivity is still challenging toward the suggested applications. However, we found that the addition of copper acetate, copper salt, can be magical to improve sensors' sensitivity and selectivity toward hydrogen sulfide detection. Here we tested different sensors that prepared from nanocomposite varied in components ratio. And remarkably, these sensors became very sensitive to lower than 100 ppb gas concentration. And actually, we couldn't identify the exact gas concentration because of the limitation of Figaro reference sensor, which has a detection limit of 100 ppb. In addition to the enhancement in sensors sensitivity, also the response time decreased from minutes for the previous sensors to seconds for the modified sensors. In the other side, these sensors showed enhancement in selectivity. For the standard sensors without copper acetate, they showed some sensitivity to 1 ppm of ammonia. And by addition of copper acetate for the modified sensors, the sensors not only showed a reduction in their response to ammonia, but they showed enhancement in their sensitivity toward hydrogen sulfide detection. These sensors showed a high, astonishing chemical and physical properties. So for example, they maintain their ultra sensitivity to low gas concentrations even after being incubated at high humid levels for 2 and 6 weeks before their exposure to the gas compared to the fresh sensors. And in another experiment, these sensors maintain their ultra sensitivity even after being soaked completely in water for a few days before their exposure to low gas concentration and compared with fresh sensors, which were not touched before. Furthermore, they showed a high mechanical and thermomechanical stability. So in one of the experiments, they showed a high mechanical stability up to 70 bending cycle at 30 degrees bending angle. And also, they showed a good thermomechanical stability in various human environmental temperatures ranging from -40 to 40 degrees, which indicates the ability to use these sensors in different environmental conditions and in different harsh environments. In addition to the sensor development, we investigated the development of the sensing mechanism, which can help us to engineer our future sensors. For the standard sensors, which doesn't contain copper acetate, the sensing mechanism, the sensor's response depended on chemical sensing mechanism, which depends on the sulfuration or partial sulfuration of iridium oxide nanoparticles to form iridium sulfide nanoparticles, which is conductive material and responsible for reduction in the electrical resistance. For the modified sensors, the enhancement in the sensor's performance, it is attributed to the enhancement, to the contribution of both the chemical and electronic sensing mechanism. So now we know that the chemical sensing mechanism depends in the sulfuration or partial sulfuration of iridium oxide. For the electronic sensing mechanism, it depends on the formation of the copper sulfide by reaction of copper acetate with hydrogen sulfide molecules. The formation of copper sulfide can form a Schottky contact with iridium oxide nanoparticles, which can enhance the hydrogen sulfide reactions in the sensor surface with the contribution of the adsorbed oxygen molecules, which release electrons in in the sensing thin film, and because of this, it's called electronic sensing mechanism. Briefly, we think that we developed a simple preparation procedure to produce flexible hydrogen sulfide sensors. They are highly sensitive to low gas concentration lower than 100 ppb, and their response is in second. They are highly selective to hydrogen sulfide gas. They are resistant to humidity change. They have a high chemical and physical stability in harsh environments. And also, they showed a high mechanical and thermomechanical stability that make them applicable in different conditions. And they are very cheap because these graphite, polystyrene, copper acetate are very cheap materials, which are occupying almost 50% of the nanocomposite. At the end, I want to thank the financial support from Green Electronic Network, NSERC, METEX, Prismic, and the research centers, LACIM, NANICAM, CKMF, and my advisor, Ricardo Izquierdo, for his support and for your attention. Thank you so much.